Before we went through the definitions of group velocity and phase velocity, we watched this video where we have an envelope with some carrier frequency underneath, and we watch the envelope propagating along at the group velocity while the ripples underneath are moving at the phase velocity. Now what I want to do is consider what happens if instead of having a single frequency under the envelope, we have multiple frequencies. So to flesh out this example, we're going to have 3 pulses with 3 different frequencies. Each of these pulses has the same envelope, and each of them are narrowband. And by narrowband, what I mean here is that the period of the carrier underneath is much, much smaller than the width of the wave, so that the length of the wave is much bigger than the oscillations underneath. There are many oscillations underneath the envelope, in other words. So these are what we call narrowband pulses. When we add them together, we get something where the envelope has the same shape and width, although it's been scaled. The height is now 3 times bigger because we're assuming here each of these pulses has the same height. If we give them each unit height, then the height here of this envelope must be 3 times bigger. Underneath we have a bit of a mess because we have beating between these 3 different frequencies. So it looks pretty messy, but there's still an envelope and there's still frequencies underneath this envelope. What's going to happen when you put it into the dispersive medium? The wave propagates and the 3 frequencies separate into their respective groups because each of those pulses has a different phase and group velocity. Each of them is narrowband. They're narrowband because the pulse is long compared to the period of the carrier underneath. The other thing we notice about the way these pulses travel is as they separate, they don't influence each other. Each pulse travels as it would have in the absence of the other pulses. So this is what linearity brings. Linearity means that we can take the separate solutions for each of these pulses and add them together, and there's no interaction between the pulses at all. Now, in this example here, we've separated 3 different frequencies in time because they're traveling at different speeds. This dispersion is exactly the same effect that makes rainbows, except that the dispersion that makes rainbows is angular because the different colors of light, that is the different frequencies, they travel at different speeds in the glass, which gives you different angles via Snell's law. But it is the same effect, it is just dispersion.